Now, what does an attacker have? An attacker has this G to the A, has G to the B, and has G. And the question is, can they compute? Can the attacker, from this information, can they compute the shared secret? If they can, then the whole system is worthless. It isn't actually a shared secret if anyone else who has this public information can compute it. But it doesn't look like, but what it seems like is that they can. So attacker has these. Can they compute G to the AB mod M? And the answer is, and this doesn't usually happen in math, but it doesn't seem so. So what do I mean by this? So it turns out mathematicians have been thinking about this, a lot of smart people have been thinking about this for a long time, and no one has come up with a way to do this efficiently. At the same time, no one has been able to prove that it's not possible. So it's actually unknown, but it's just assumed that this is kind of hard. It's worth saying that if any of you guys, who I'm sure are very clever, if you can figure out a way to do it, then you can break the internet. So you can break security on the internet and prevent anything from happening until a new system is brought online. So if anyone has delusions of grandeur, here's a great problem for you to work on. You need to try to, given this information, to compute G to the AB model. And it's a hard problem because, as we see here, these powers look to be random. If all you knew was the output, how could you figure out what the corresponding power was? It seems like the only way to do it is just to try all of them. And so what I want to mention is that to make this work, so to prevent what's called a brute force attack, you need to make sure that the numbers involved are really big. So A and B and M should be big. So to finish off my talk today, I want to mention one last thing, which is how big is big. So one last thing to talk about is how big should this be? So here's one idea. Here's one example of what might be. Got it. Oh, wait. Oh, okay. Sorry, I just got it.
as long as you
Yeah, I guess so. Okay. Okay, so let's see. So here's an example of some, yes, okay. So let's talk about big numbers. So here's an example of a big number. Number of particles in the universe. About 10 to the 87. So that's a pretty big number. If you counted up every single atom, if you think about the things that we're sitting on, right? I mean, they're made of atoms. And you think about not just in this room, but the entire world. And if you think about just not in this world, but in the entire universe, how many total particles are there? Now, this is one estimate that I got online last night. So I looked online, there's just one estimate of how many particles are in the universe, 10 to the 87. So that's one example of a big number. Here's another big number. So if you took the number of computers in the world, and I'm estimating how many computers are in the world. I don't know, I was thinking a billion, but maybe we should go 10 billion. There's, what, 6 billion people in the world. Do you think each one has a computer by now? Maybe not quite. So maybe a billion computers. So let's say 10 to the 9th computers. That's a billion. And then, how fast is a computer these days? So a computer can do. So it's about these days about 3 point some odd megahertz means that you can do billions of operations per second. So let's say about 10 to the 10th instructions per second. And so what we're trying to estimate here is how big should we make these numbers to make sure that an attacker can't break our system by brute force. So now let me ask, how much time are you willing to wait? So if I told you, here's a program, just run it, and at the end of it, you'll have some sensitive information. You'll have your friend's credit card number. How long would you be willing to wait? Maybe a year, I don't know. Maybe a couple of months. Maybe you're really impatient. Maybe only a couple of minutes. But I mean, let's suppose that you were willing to wait the entire length of your life. So let's suppose we were willing to wait that long, say 100 years. So 100 years. 100 years is about 10 to the 10th seconds. So now we can have an estimation of about the number of operations that we could do. Let's imagine that we have possession of all the computers in the entire world, that each one of them is pretty fast. This is about the fastest computer that runs today, including powerful supercomputers. So let's suppose that every computer in the entire world you had access to, and each one was as powerful as the most powerful supercomputer, and that you were willing to wait 100 years for this computation to run, then the number of instructions that you'd be willing to do would be about 10 to the 10th times 10 to the 9th times 10 to the times 10 to the 10th times 10 to the 9th, which is about 10 to the 29th, or let's call it 10 to the 30th. So that's maybe an estimate of how big we need to make. How big should we make these numbers to prevent someone from attacking it by brute force? Here's an estimate, about 10 to the 30th. If we make it that big, then that should be, well, okay, let's put a margin of error in there, right? So 10 to the 30th is maybe big enough, so let's square it. Let's make it 10 to the 60th. Now this sounds like a pretty big number, but what's interesting is that for a computer, computers can handle numbers that are this big really, really easily. Because for a computer to store this number, takes log base 2 of 10 to the 60th bits. Because if you think about a number, the way that you represent it in binary is with bits. And this is the number of bits you need to represent a number that's this size. And we can use our properties of logarithms. So by properties of logarithms, log base 2 of 10 to the 60th is 60 times log base 2 of 10. Log base 2 of 10 is a little bit over 3. So 60, 120, 180, call it 200. So roughly 200 bits. Well, this is no problem. I mean, the RAM on my computer is, I keep forgetting if it's mega, no, it's giga, right? So megas, million, billion. So, just the RAM on your computer right now is in billions of bits. So holding a number that's 200 bits long, I mean, that's no problem at all.